Hello and welcome back to another Chemistry Academy video. In this video we are going to be looking at equilibrium in the context of the Higher Chemistry course. If you are studying advanced higher chemistry, this would still be helpful for you just on the theory behind equilibrium. So equilibrium, it occurs in any reversible reactions, so any reactions in which there's a forward and backwards reaction going on at the same time, you will get an equilibrium being established. So equilibrium is essentially, it's known as dynamic equilibrium because the system is still moving, but if you were to look at the reaction in terms of what's being produced, what's being used up, it looks like nothing's happening because there's no change in the amount of products you have or the amount of reactants you've got left. However, the reactions are still proceeding, the forward and backwards reaction, but the rates of the forward reaction is the same as the rate of the backward reaction. So it looks like there's no change, that the reaction is not still going on, even though it is. So it's a bit like if you were sitting in a ball pit, chucking balls out of the ball pit, and then there was someone there throwing the balls back in. You might start chucking the balls out quicker than they're throwing them back in, but it might get to a point eventually where you're throwing them out. So you throw one out and they're throwing it straight back in. So there's no change to the number of balls in the ball pit at that point, because as quickly as you're throwing it out, the other person's throwing it back in. And that's essentially the way that it works with dynamic equilibrium. So at dynamic equilibrium, the rates of the forward reaction is equal to the rate of the backwards reaction, and the concentrations of the products and reactants are constant, so they're not changing, which is why it looks like the reactions may be finished. There's a couple of graphs that you quite often see in relation to equilibrium. So if we look at rate versus time, the forward reaction starts off really fast and then it will start to slow down as the reactants are used up. And then the backwards reaction starts off at a really slow rate because there's no products to break down initially, and then as the more products are produced, it'll start to speed up. When the rates start to become equal, that's when equilibrium is reached. So the first point that the reaction rates are the same, that's where equilibrium has been established, and then it remains in equilibrium until you make a change on the system. We'll look at the changes in a minute. If we've got a graph of concentration over time, our reactants are going to start off with a high concentration because they've not been used up yet, and then as the reaction proceeds, the concentration of those is going to decrease. For the products, we don't have any products at the start of the reaction, and then eventually we'll make some, and so they'll increase. Equilibrium is reached when those concentrations no longer change, so when the line starts to go flat. So roughly, based on my bad drawings, equilibrium would have been reached at this point, and then again it stays in equilibrium until you make a change on the system. Okay, so the main things to remember are that at equilibrium the rates are equal and the concentrations are constant. It's very rare that the concentrations are the same, and usually there is more product in the reactant, but that isn't always the case either. It just depends on what the reaction is. But in an ideal world, in terms of maximising yield, you'd want to have more product than you do reactants. In relation to what this means in terms of the equilibrium position, if you have more products at equilibrium than reactants, then we would say the equilibrium sits right on the right. If you have more reactants than products at equilibrium, then we would say the equilibrium sits on the left because there's more of this stuff on the left hand side. So when we talk about equilibrium moving right or left, that's what we mean. Is it moving to the product side, or there being more products than reactants, or is it moving left to the reactant side where there's now more reactants than products? So we're going to get into the factors that can shift the equilibrium now. So yeah, we'll get to that. So let's have a look at the factors that affect the position of equilibrium. It is very specific to the reaction that you're given, so I've tried to generalise it as best as I can, but I'm going to explain it in the context of the Haber process. So if you get an open-ended question on equilibrium, then the Haber process is a really good one to use as an example because it's not a hard equation to remember. It's nitrogen and hydrogen forming ammonia, and it basically in the Haber process they take into consideration all of these three factors. when they run it in order to maximise the yield. So it is a good one to pick if you are looking for a specific equilibrium example for an open-ended question. So the three things that can affect the position of equilibrium are concentration, temperature and pressure. And like I said before, the position is just whether at equilibrium do you have more products than reactants, or do you have more reactants than products. Usually we're wanting to have more products than reactants because that's going to make us more money if we're selling the product. However, there are some cases where if it's a reaction we don't want to happen, that's producing something that's toxic or harmful, in that case we would usually want to shift the equilibrium to the left, where we have more reactants and less products. So that's usually if the products are harmful, we would do that. So if we look at concentration, equilibrium shifting change basically is called Le Chatelier's principle. Really good at French. And you don't ever have to say his name in the SQA exam, so don't worry about that. But basically, he did a lot of investigation on equilibrium and discovered that if you make a change on a reaction, once it's reached equilibrium, the equilibrium position will shift to counteract that change. So I always use the analogy that it's a bit like an annoying sibling, where it'll just constantly undo anything you do. So let's say you go and tidy up your room, your annoying sibling will come in and just mess it up again. So that's how equilibrium shifts work. So if you increase the concentration of something, then it will shift to remove them. So if we add more nitrogen and hydrogen into the reaction, the equilibrium will shift to remove those things, so it will shift away from that side, so it will shift right, and then end up making more ammonia in the process. So when you're talking about the shifts in the extended response, you would want to give the direction of the shift and then state which reaction that's then increasing the rate of. So if it's shifting right, it's increasing the rate of the forward reaction and producing more of your product, and then you'll have less reactant at the end. If you add more product to this side, then the reaction will shift to remove it, so it will reverse and it will favour the backwards reaction. I've just realised I've not even put a reversible reaction symbol here. Okay, so you add something, the equilibrium shifts to remove it, so it'll shift in the opposite direction. If you remove something, the equilibrium will shift to remake that thing. So if we remove ammonia, then the equilibrium will shift right in order to make it again. So when I'm looking at equilibrium, I actually do two things. So if I'm adding something, I'll circle the thing and then draw an arrow going away from it. Okay, because if I circle it, I'm telling myself I'm putting more of that in. So then I'll draw an arrow to show the equilibrium shifting away from it. And that will show me the equilibrium shifting to the right. If I'm removing something, what I tend to do is scribble it out, and then I draw the arrow towards it to remake it. So again, if we move ammonia, that's going to shift the equilibrium to the right and increase the rate of the forward reaction, which will then produce more ammonia. Okay, so when you're giving your answers, that's the things you want to cover: the direction of the shift, which reaction rate's increasing, and then therefore do you make more or less of something. Okay. When it comes to, I'll give you an example after this actually, there's one to specifically look out for when it comes to concentration, so we will look at another more complicated example of that afterwards. But if we just move on to temperature, so temperature, the main thing to try and remember for this is intendo, so that stands for an increasing temperature favours the endothermic reaction. So if you just remember that, you'll be able to work out which way the equilibrium is shifting given any reaction. So you will be given the enthalpy change if you're having to consider temperature effect on equilibrium. So the enthalpy change that's given is always for the forward reaction. So this is telling me that the forward reaction is exothermic because it's got a negative enthalpy change. So that means if we increase the temperature here, it's going to favour the backwards reaction because the backwards reaction is endothermic. So if your forward's exo, your backward will be endo, and vice versa. Okay, it's always just the opposite, like you learned in Hess's law. So If we increase the temperature, it's going to decrease the yield of ammonia because the forward reaction is exothermic. So an increase in temperature would favour the endo, which is the backwards reaction, and therefore you would have less ammonia and more nitrogen and hydrogen. If we were to decrease the temperature, that would then therefore favour the exothermic reaction. So a decrease in temperature would shift the equilibrium to the right, increase the rate of the forward reaction, and therefore produce more ammonia. Okay, and like I said, it really just depends on the reaction you're given. So just remember intendo, look to see what the forward reaction is, and yeah, the increasing temperature will favour the endothermic one. A decrease in temperature will favour the exothermic. In the terms of the Haber process, they constantly feed in nitrogen and hydrogen, and they constantly remove ammonia. So in terms of concentration, the equilibrium is constantly being shifted right. They also run the reaction at as low a temperature as possible because it's an exothermic process. So as low temperature as possible to maximise yield, to shift the equilibrium right in that case as well. Quite often as well, you will be given a graph that looks like this, where you've got yield versus temperature, and it'll show the yield decreasing as the temperature increases, and they'll ask you what you can conclude from the enthalpy change of the reaction based on that. So if your yield is going down as the temperature goes up, that means it's an exothermic reaction, because like we said, an increase in temperature would favour an endothermic reaction. If it was the other way around and the yield was going up with increasing temperature, then that you could conclude that it's an endothermic reaction. So if you are asked for a conclusion on the enthalpy change of a reaction based on a graph that shows you the yield, again, just remember intendo. And if it's going up as the temperature increases, then it's an endothermic reaction. If it's going down, it's exothermic. So lastly, pressure. Now pressure only affects moles of gas. So you would really have to count up here how many moles of gas you have on each side of the reaction. Let me just write this. So if you increase the pressure, the reaction is going to shift to reduce the pressure again, and the only way it can reduce the pressure is by creating less gas, because it's the gases that are causing the pressure really. So an increase in pressure would favour less moles of gas, and then therefore a decrease in pressure would favour more moles of gas. So if you drop the pressure, the reaction can increase the pressure again by making more gas. If the reaction has the same number of moles of gas on both sides of the reaction, pressure won't affect the position of equilibrium because there's nowhere for it to shift, to change, to undo the change you've made. So if we look at the Haber process, it's got 4 gas moles on this side, 1 nitrogen, 3 hydrogen, and then there's 2 gas moles on this side. So I'm looking at just the big numbers here. Okay, so if we increase the pressure in the Haber process, that favours less moles. So high pressure favours less moles. So that would shift the equilibrium to the right and increase the rate of the forward reaction, therefore making more ammonia. If we decrease the pressure, that favours more moles, so it would shift the equilibrium to the left, increase the rate of the backwards reaction, and produce less ammonia. Okay, so just remember, high pressure, less moles, low pressure, more moles of gas. So if anything's not got a G state symbol, it doesn't get counted in your recount, and I would advise writing the numbers above the reaction as well. Okay. The effect that catalysts have on equilibrium is pretty basic because they don't have an effect on its position at all. That's because they increase the rate of the forwards and the backwards reaction in equal amounts. So there is no change to the position of the equilibrium because it's not increasing the rate of just one reaction over the other. However, you will get to equilibrium quicker. So to put that in like a picture context, if we look back to the graphs before, equilibrium is reached when the rates are equal. So in this case is here. That would be, for example, if you didn't have a catalyst in your reaction. If you did have a catalyst in your reaction, equilibrium would be reached a lot quicker, okay? But it still reaches equilibrium and it's still in the same position. Okay, so you don't get any more reactants or products, you just make the reaction reach equilibrium faster. So there's no change to its position, it's just reached more quickly. So we're going to finish off just with another contextualised example, more so focusing on the effects of concentration. This is the sort of way that you'll get it in the multiple choice questions in the exam. So we've got this reaction here, it's given us an enthalpy change as well. Remember, this is for the forward reaction, so we know from this that the forward reaction is exothermic, so that means the backwards reaction will be endothermic. But we're going to look at how changing or adding these things to the system will change the equilibrium position. So if we add NH3, that means that we are adding in more of this, so it's going to shift in order to remove it. So if we add more NH3, it's going to shift right, increase the rate of the forward reaction and make more products. If we add sodium hydroxide, so we're going to, if you're given anything ionic, the best thing to do is write down the ions that are going to be added. So sodium hydroxide is Na plus and OH minus. So we look to see if either of those are in the reaction. So sodium ions aren't in there and they usually don't interfere with anything, so they're not going to make a difference. The hydroxide ions, they are in here, so if we're adding more of these, it's going to shift to remove them. So in this case it will shift left, increase the rate of the backwards reaction, and therefore result in less products. I'll write all this down afterwards. So then if we add HCl, that's adding H plus and Cl minus. So if we look, there's no hydrogen ions in the reaction, there's no chloride ions in the reaction, so it would look like it's not going to have an effect. However, what you have to remember is that hydrogen ions and hydroxide ions exist in an equilibrium of themselves in order to produce water. So what actually happens is the hydrogen ions react with the hydroxide ions in order to form water. So hydrogen ions will actually remove hydroxide ions from a reaction, which means that in this case it would shift the equilibrium to the right in order to remake them. Okay, the opposite thing happens as well. If you've got hydrogen ions in your reaction and you add in hydroxide, then they will remove the hydrogen ions, so the reaction will shift to remake them again. Okay, so that's one to watch out for, that hydrogen ions will remove hydroxide ions and vice versa. If we look at the potassium nitrate, so that's adding K plus and NO3 minus. So there's no potassium, no nitrate, neither of them really interfere with anything, so that would have no change on the equilibrium position. Okay, if you are doing a multiple choice question and you're struggling to find the correct answer in this, always check, you can check the solubilities table as well, because sometimes it might be the case that the nitrate bonds with the ammonium to form a precipitate, so something that's insoluble. So you would look up to see if ammonium nitrate was soluble or not. It is, so it's not going to remove anything, but if it's solid, then it means the ions are being removed from the solution, so it's like decreasing the concentration. But they don't put that in very often. It is mostly the hydrogen ions and hydroxide ions that you really need to watch out for. So if we look at the effect of temperature and pressure on this equilibrium as well, so if we increase the temperature, remember intendo, increased temperature favours endothermic reaction. The forward reaction is exothermic, which means the backwards reaction is the endothermic one. So if we're favouring the backwards reaction, then the equilibrium is going to shift left and increase the rate of the reverse or backwards reaction, therefore you'll have less products. If we decrease the temperature, that's going to favour the exothermic reaction, which is the forward one. So a decrease in temperature will shift the equilibrium to the right, increase the rate of the forward reaction and make more products. When it comes to pressure, we're only looking at gases. So if we total up the gas moles on the reactant side, there's only 1 mole of ammonia. And then on the right hand side, on the product side, there's no moles of gas. So if we increase the pressure, that favours less moles of gas. So that's going to shift to the right where there's less gas, and then therefore increase the rate of the forward reaction and produce more products. If we decrease the pressure, decreased pressure favours more moles of gas, so it's going to shift to the side with more moles of gas. So decrease in pressure would shift the equilibrium to the left and cause an increase in the backwards reaction rate, and therefore you would have less product. Okay, so I'll write all that up as well for your notes. But yeah, so hopefully that gives you a good idea of how equilibrium and its position change actually works now. If you did find this useful, please give it a like and don't forget to subscribe. I'll see you again soon.